We'll proceed in vector summation and integral calculus. Vector summation and integral calculus, the topic in which we are pursuing the discussion. Vector summation and integral calculus. Right now we are pursuing discussion in Taylor series. So how I can go with the Taylor series without the proof what Mr. Taylor or Sir Taylor he has suggested the bringing any algebraic equation, bringing any algebraic equation in terms of series of polynomial equation. What is polynomial equation? X to the power n is polynomial equation. What is monomial equation? X to the power 1. That is monomial equation. Binomial equation, binomial, trinomial, these are the, like if I have two variable x and y, then more or less it is considered as binomial equation. So if someone has polynomial equation will be like x square, x to the power 3, x to the power 4. Can we describe any function? What is your function? Log x. Log x is the function. E to the power x. E to the power x is a function. Okay, what are the other functions you have? Well-known function, sinusoidal function, and then a logarithmic function, exponential function. There can be other functions also, or combination of all these functions, like sin x plus log x into tan x multiplied by e to the power x, and then plus e to the power theta I. These are theta x. I'm sorry, e to the power ix. These are the complex equation. Any equation can be written in terms of polynomial equation. This is what Sir Taylor, Mr. Taylor is saying. Okay, something like if someone has sin x, then sin x can be written. Sin x can be written. There are other stories also where anything can be written in sinusoidal wave also. Reverse is also true. Means if I have a square wave, the square wave can be written in combination of many sinusoidal wave. If I have many sinusoidal wave of different frequencies, okay, Fourier transformation and those things comes into the picture. If someone has sinusoidal wave of different frequency and someone combines it, then it would make a square wave. It is also possible. Anyway, we are not discussing about it. We are discussing about any wave. Any wave means any algebraic equation, sinusoidal, logarithmic, or any complex equation can be written in a form of a0, that is a constant. It is not a variable. A0 into x to the power 0, or in Sir Taylor's form A0, A and subscript 0, A subscript 0 into x minus A to the power 0. That A and this A is different. This is A0 and that is A. X minus, this can be said x minus alpha whatsoever, x minus A to the power 0 plus a1 x minus a to the power 1 plus a2 x minus a to the power 2 plus a3 x minus a to the power 3. This is what Sir Taylor is saying, that this is one of the most precious invention happened in the mathematics arena. And Euler's formula, that is e to the power I theta equal to cos theta plus I theta, is derived from the Taylor's expansion only. Okay, so Taylor is a person who started a very different discussion, very different discussion. Any algebraic equation can be termed into series of polynomial equations. How to find a0? To find a0, substitute x equal to a, fx equal to function over x equal to a0 plus a1 x minus a to the power 1 in bracket x minus a to the power 1, a2 x minus a to the power 2, a3 x minus a to the power 3, like that. If I set x equal to a, everything will become 0 and a0 will remain. a0 equal to fx at x to the power at x equal to a. Similarly, if I take single derivative, then a0 term will go away and only a1 will remain, other will become 0 at x equal to 1 a. If I take double derivative, then a0 a1 will go away, only a2 will remain, other will go away at x equal to a. Like that, we can find the value of A0, A1, A2, A3, A4, and finally we can say that our values are ready the way we were saying, and then we have a kind of any, if I have any algebraic equation, then we have representation as a polynomial equation. A0 plus A1 x minus a to the power 1 plus A2 x minus a to the power 2 plus A3 x minus a to the power 3 and so on. Okay. Now question is arising that and this proof we did through the kind of n division area. Okay, if I take fx dx, okay, someone say I have a formula fx dx. I have a formula fx dx. How we proved it? If this is x-axis and this is y-axis, consider this is the fx. Fx can be anything. The way it is falling, it can be, I believe, fx equal to minus x square. I think so. Minus x square, no? It can be some constant minus x square. Okay, when x equal to 0, constant will come into the picture, and after that it will start decreasing like this. Up. Yeah, it will start decreasing in x. But it can be any complex equation fx. Okay, what is the how I can represent this fx in terms of series of polynomial equations? The fundamental what we have provided is calculate the area of the fx, that is fx dx. Integration from 0 to x. Consider this is x, this length is x, and this is x-axis. This length is 0 to x, and here the height is function over x. This is function over x. This is function over x-axis, y-axis. Height here is function over x at x equal to 0. What is the area of this fx dx? Fx dx integration equal. Okay, first we will calculate the simplest thing. That is the f0. What is the height? At this height, if I multiply by this width, then it will give this area. And this area is x into fx at x equal to 0. It will go like this, and it will make a rectangular area where the top is flat minus, because this area we calculated extra. If I calculate a rectangular area, so fx dx integration equal to fx at x equal to 0 into x minus this area. This area we calculated extra. If I say f0, if this is the function at x equal to 0, this is the height. Height into x is this rectangular area. This rectangular area, if we talk about this rectangular area, then this rectangular area is this area, what is the desired area plus this area. This area is extra we calculated, so I have to subtract this area. Then I can say, let's think that this is a slant line and flat line. This is not a curved line, slant line. If I consider this is a slant line, then what is the area of this side? Then the area of this side is the slant line. If the slant line slope is dy by dx. If I take any point, slope at any point, okay, if someone focus it here, then we will go for 3D. Okay, if someone is focusing slant line, then everywhere the slant line is different. Slant line is tangent line. If I take x equal to 0, then this is the tangent line. If this is the tangent line, dy by dx, at any moment it will be a tangent line. If I say tangent line at x equal to 0, this will be tangent line. This tangent line it makes, and this side, it makes a triangle here. What is area of this triangle? The triangle area is this vertical multiplied by horizontal by 2, because it is a triangle. 1 by 2, this vertical is dy by dx at x equal to 0 multiplied by x. This will give the vertical. So 1 by 2 dy by dx, or dfx by dx at x equal to 0 into x. That will give the area of the triangle. And someone would say you missed something. If you calculate this triangular area, still you're missing this part, because first, so I'm saying the fx dx integration, that is this area that we want, equal to the first rectangular region, that is fx at x equal to 0 into x plus plus, I'm sorry, minus the triangular area 1 by 2 dfx by dx at x equal to 0 into x, that is the height, into x. Okay, then I have to subtract this portion also, because if I draw a tangential line, then this portion is remaining that I have to subtract for the first rectangle that I calculated. I thought this rectangle will be the area what we want. Then I saw this is the extra. Then I draw a triangle and then saw if I subtract, then I'll subtract everything, but it is not possible. Then I'll take little more curve. First I took this curve. I'll take little more curve and try to find out the area. Then this area will be the for a curve that is the x square. First I took tangential line, that is x. Now I'll take another, that is x square. The area for the x square that we have seen is 1 by 3. If I take first differentiation dfx by dx, then it will lead into a tangential line. If I have a fx equal to x square, a line like a curve, fx equal to x square, a line like a curve like this. This is fx equal to x square. Considering this is x-axis, this is a parabola, or upside down. This is also a parabola. This is what we are talking. If I say this is x square, okay, if I do the first differentiation of fx equal to x square, then it will lead into a slant line dy by dx. If I go with second differentiation, then it will lead into a flat line. That flat line multiplied by the x will give the area. But by then we have to take two differentiations. First differentiation, first differentiation will lead to division by 1 by 3, and second differentiation will lead by differentiation division by 1 by 2, because after first differentiation whatever remain, that is a function of x, and then I have to differentiate it again and divide by 1 by 2. That will be more or less area of a triangle. Whatever comes, then I have to multiply with the x to have the area of the rectangle. Means the area of the second degree, if I take derivative, it will be 1 by 3 dfx by dx into x. Okay, dfx by dx I have to differentiate again. 1 by 2 d2fx by dx square into x. Whole I have to multiply with the x, and it will give the area. That I have to subtract again. Keep doing like that one. Keep doing like that only. Okay, if I'm trying to calculate area, area is reverse of differentiation. If I have differentiation, if I have a formula x square, if I'm trying to get double derivative, then whatever is the exponential x to the power 2. 2 is the power. Power will come as a coefficient. X to the power n, if I differentiate 2 times, it will become n into n minus 1 into x to the power n minus 2. 2 time differentiation will bring the coefficient 2 times outside. Okay, in that fashion, if I'm trying to calculate area and then going by the dual differentiation for the integration term, that is the area, it will come as denominator 2 times. Makes sense? If I have a polynomial, if I go for double differentiation, whatever is the power will come as a numerator coefficient 2 times dual differentiation. Similarly, if I am involved in dual differentiation in order to calculate the area, then area, since it is dealing with the integration, the dual differentiation will lead into the area calculation as 2 times coefficient as denominator. Okay, so if I have a formula at x square and I am doing differentiation 2 times, if I did 1 time, people remember calculating the area of a triangle. If I did that differentiation 1 time, then 1 by 2 came into the picture. That is the area of a triangle whatsoever. If I do 2 times, considering equation of the curve is x square, then 1 by 3 into 1 by 2, that will come as denominator. More or less, it will be 1 by 3 factorial into d2fx by dx square at x equal to 0 into x to the power 3, x square into x to the power 3. Like that, that will come as the Taylor series. This is our proof, and it is not available in any book. We will think about how to publish it. Okay, in that fashion, what is the area of this shape? If I talk about area of this shape, then what is area of this shape? Fx dx integration, that is the area, equal to fx at x equal to 0 into x plus 1 by 2 dfx by dx at x equal to 0 into x square plus 1 by factorial of 3 d2 fxy by dx square into x to the power 3 d2 fxy by dx square is a dual derivative of x equal to 0 plus 1 by factorial of 4 d3 fxy by dx 3 at x equal to 0 x to the power 4 plus like that. If I differentiate both sides, left side I get fx. We want fx. Fx dx integration 0 to x will give fx only. Fx equal to, first is fx at x equal to 0 into x. It will become f0. Second will become dfx by dx into x. X square differentiation will 2x, 2 to go away. Dfx by dx at x equal to 0 and then into x plus d2 fx by dx square by factorial of 2 into x square. X to the power 3 differentiation will be 3x square. 3 go away plus d3 fx by dx cube at x equal to 0 into x to the power 3 by divided by factorial of 3. Earlier it was factorial of 4. X to the power 4 differentiation is 4x to the power 3. 4 will go away. Like that. This is exactly the Taylor series. So Taylor series is perfect, but we have proved by dividing our calculation of area and dividing the area into n different parts and start calculating the area with the complexity. First is we take the flat line calculating the rectangle plus second we take a slant line and calculating the area of the triangle. Make sense? Then third is taking x square and then calculating the area, then with dual differentiation. Fourth will be x to the power 3, fifth will be x to the power 4. Like that, and we at the end we will actually calculate this underneath area when we will subtract triangle and then x square x to the power 3 x, like that we will complete it. Okay, someone would say it is negative. Negative can come. There is nothing like that. Negative can come. Negative, positive is not very different. Depends upon the direction or something like that. Anyway, now question is arising how we can find with for the three dimension. How we can find this for the three dimension. Okay, to calculate the three dimension, now we have something like to calculate the three dimension. Okay, we have something like, consider this is xy plane. This is xy plane. This is x-axis and this is y-axis. This is xy plane. And I have a flat surface on top of it. This surface is exactly parallel to it, and it has a width of x and length of y. It is kept on the xy plane like this. What is the volume underneath this? Okay, what is equation of this flat line? If this is surface, then this is 3D. 3D, the equation of surface is fxy. Fxy means z, that is the height. Fxy equal to something. What about if I want to calculate the volume under the fxy? Then fxy d of xy or dx dy. F function over xy, fxy dx dy. Integration over the xy plane. This, if it goes and make intersection on xy plane, where the along x-axis it is x and along y-axis it is y, then it is integration of x is 0 to x, y is 0 to y, fxy dx dy. This is the volume. Okay, let's calculate the volume through raw way. So volume is fxy dx dy and the integration where xy starts from the 0 and then means the begin point of the surface. If I consider this as the begin point of the surface, then this begin point, if I go down, it will hit the origin 0, 0, 0. At this point, what is the height multiplied by this x and this y? Okay, that is the volume underneath it. So I can say fxy at x equal to 0, y equal to 0. What is the height at that point? Multiplied by x and y, that is the volume. So fxy dx dy integration, that is the volume, equal to f xy at x equal to 0, y equal to 0 into xy. Makes sense? Okay, someone would say, who's told you that it is a flat surface? Actually, it is not a flat surface. It is a this surface. Okay, little bit tilted. Okay, it is analogous to what we were talking in terms of it is analogous to what we are talking in terms of 2D Taylor series. 2D Taylor series, if I had to calculate the area underneath it, first we took the rectangle, F0 height multiplied by width, full rectangle. Then I started subtracting like this. So someone can consider the flat surface that we are talking, this is the XY plane. Consider this is the flat surface above it. Then it is something like a twisted surface. It is not a flat. It is something very highly convoluted surface. The way it is if I have a curve length, then this is highly convoluted. It is convoluted to any degree. It is not even y equal to x, not even y equal to x square, not even y equal to x to the power 3. It is y to x to the power n. That much it is convoluted. Okay, if I talk about sinusoidal wave, then I don't know this wave. This is y equal to x. If I say, then it will be tangential. Y equal to x square. If I say, then it will be like this. Y to x to the power 3. I'll x square say, then it will be like this. Anything means looks like this curve holds polynomial of many degrees. That degree that would have hinted Sir Taylor that it can be summation of that. Anyway, now similar fashion, if I talk about a surface, it may not be flat. It will be convoluted to any degree. But for simplicity, first I have calculated the volume of the flat. Okay, then I'll go to the next degree. Okay, so I'll go to the next degree. What is the next degree? If I talk about the next degree, then I'll make it tilted like this and then like this. What I'm trying to say is, up to here I have calculated the volume. Consider the actual surface is like this. Then, then here, this is the x equal to 0, y equal to 0. This is the height. This is the xy plane. And this is the origin. If this is the origin, then this point is x0, x0, y0. This is the height fx, y at x0, y0. This height, we calculated the volume. This height, we calculated the volume. This region is separate. Understandable, right? So if this is the flat surface on top of xy plane, then I have calculated the volume. But it is like this and like this. Then this is the volume we calculated. This is the volume we calculated. Now whatever is being seen here, this is the extra. What is this extra? Consider this was the surface, original surface. Then from here, that is the this flat surface underneath volume we calculated. Then plus whatever extra we are seeing here. What is this extra? Now if I keep y-axis constant and move x-axis, this is x-axis, this is y-axis. If I keep y-axis constant and move the x-axis like this, then what is this forms a triangle. This forms a triangle. What is volume here? This triangular region into y. This is the y length. Triangular region into the y will be the volume. What is the triangular region area? This is z, that is the height. This is x and this is y. Okay, if I say at x equal to 0, y equal to 0, what is dz by dx in zy plane? Zx plane, what is dz by dx? If I know dz by dx at x equal to 0 and y equal to 0, multiplied by x, then it will give this height. This height multiplied by x by 2 will give this triangle. So this triangle area is 1 by 2 dz by dx at x equal to 0, y equal to 0, or dfxy by dx, fxy is z, dz by dx at x equal to 0, y equal to 0 into x means 1 by 2 dz by dx at x equal to 0, y equal to 0 into x square is the area of the triangle multiplied by the y will be the extra volume. Similarly, if I keep x constant and move the y, then what will be the volume? Then this is the triangular area multiplied by the x. 1 by 2 dz by, this proof is not there in any of the book. 1 by 2 dz by dy into dz by dy into y square into x. What will be the net volume extra what we are saying? First we move like this and like this. This is the extrapolation. That will be addition of both. That will be 1 by 2 dz by dx or dfxy by dx at x equal to 0, y equal to 0 into x square into y plus 1 by 2 dfxy by dy at x equal to 0, y equal to 0 into y square into x. Okay, if I settle it down, it becomes 1 by 2 is dfxy by dx into x plus dfxy by dy into y in bracket x into y. Okay, what was the condition if it was a one variable? Then it was 1 by 2 dfx by dx into x square. If it is dual variable, dual independent variable of 3 dimensions, then it is 1 by 2 dfxy by dx into x plus dfxy by dy into y x into y. Is it similar to what we are showing in the single variable? 1 by 2 dfxy by dx into x looks like it is similar. The last end x, here it is x into y. That is the base area. If I talk about xy plane, then this is x axis, this is y axis. In x axis I have taken x length. In y-axis, I have taken y length. This area, one area is x into y, x into y. If I break it, whatever the assumption we are making for the separate area, the net area of the volume is fxy at x equal to 0, y equal to 0 into x into y. That is the base, that is the height, that is the volume. Plus 1 by 2 in bracket dfxy by dx into x plus dfxy by dy into y bracket close into xy. Xy is the base area. If I consider xy plane as a single independent component, then that xy is the area. 1 by 2 is also there. If I talk about the single variable Taylor series, then first expansion is 1 by 2 dfxy by dx into x into x. Last x is the base. Here last xy is the base area. 1 by 2, 1 by 2 here also. There it is dfx by dx into x. Here dfxy by dx into x plus dfxy by dy into y. Looks like whatever independent component we have x there, that can be replaced by x plus 1 here. It will be same thing, x plus 1. Okay, means if I say let's forget this. Let's go with the dual dimension multivariable expansion of the Taylor series, the way we were talking. At least with this hint I get that if I talk about similarity, then base earlier the base length was x, now base area is x into y. Earlier when we calculating the triangular region, while calculating the triangular region, we multiplied with the x, okay, into x. Here it is looks like the similarity of the x here is x plus y, x plus y. When we start breaking the x square into x and back to the flat line, then x plus y comes into the picture. Let's go with this fundamental because it looks similar. Let's go with this fundamental and come with the kind of multivariable Taylor series. Now we have volume calculation at fxy. I'm sorry, I will not go by the volume calculation. Let's go with the Sir Taylor formula only. Then what will be Sir Taylor's formula? Sir Taylor formula will be fxy equal to a0 into whatever to the power 0 plus a1 plus a1. Earlier it was a1 into x. Now it will be a1 into x plus y in bracket. I'm replacing x with x plus y. The way we are seeing the scenario. Okay, plus a2 and in bracket x plus y whole square, the way it was earlier, x square. This is our proof, it is not in the book. Plus a3 into x plus y to the power 3. Like that someone can proceed. A to x plus y whole square, x plus y to the power 3, something like this. Let's start now. Okay, set x equal to 0, y equal to 0, x equal to 0, y equal to 0. I am talking about where someone say earlier, if you remember, it was x minus a whole square, x minus a to the power 3. You have taken x plus y. Someone can take x minus a plus y minus b. Instead of I'm saying x plus y, someone can say x minus a in bracket plus y minus b in bracket and then continue. There is nothing like that. Let's take a and b as 0 only. Maclaurin series. Now fxy at x equal to 0, y equal to 0, if we calculate, everything will become 0 only. Only a0 will remain. So a0 equal to fxy at x equal to 0, y equal to 0. F0, 0. Okay, let differentiate it with x. Let differentiate it with x. What is the second term? A is 1x plus a1y. That is the second term. a1x plus a1y. Let differentiate a whole with the x. dfxy by dx. First will go away. Second will be a1 and second thing will go away. Similarly, I can break all the x plus y whole square x to the power 3, or we can break and do the first derivative with the x. Now set x equal to 0 and y equal to 0. All will become 0 except a1. A1 that was sticking with x. That a1 will be dfxy by dx at x equal to 0. Okay, in that fashion, it will become dfxy by dx into x. Makes sense? Okay, plus a1y that is remaining. Let differentiate with the y dfxy by dy at y equal to 0, x equal to 0. If I differentiate, everything will go away. Right side, it will be there. Now set x equal to 0, y equal to 0. All will again go away. Only a1 will remain. That was sticking to the y, and that is equal to dfxy by dy at x, y equal to 0. Now I can rewrite as a0 plus dfxy by dx at x equal to 0, y equal to 0 into x plus dfxy by dy at x equal to 0, y equal to 0 into y. Settle down. Now I have a2 into x plus y whole square. That will be a2 x square plus a2 into 2 xy plus a3 I'm sorry, a2 and in bracket x plus y whole square. This is our proof. Then it will become a2 and in bracket x square plus 2xy plus y square. Let's settle down the first one, a2x square. Okay, now do the dual differentiation of this. First, a0, a1 term will go away completely with dual differentiation with x. Here, a2 will remain, other will also go away. Other will be remain and set x equal to 0, y equal to 0. Okay, in that fashion, it will become like d2 fxy by dx square equal to a2. I'm sorry, it will be 2a2 x square dual differentiation 2a2. Other thing, nothing will be there. So a2 will be 1 by 2 d2 fxy by dx square. Makes sense? Now I have a2 with 2xy also. Now take first differentiation with x. Then x square will remain, x square will become 2x. And here xy was there, x will remain, x will go away, y will remain. Other y square will go away and other things will remain. Take one more derivative with y again. First derivative with x and one more derivative with y. First a0, a1 term will go away. a2 x square was the term. If I differentiate with y, that will also go away. Here it will remain as 2a2. X and y will become 1, 1. 2a2 plus all will go away. And if I set x equal to 0, y equal to 0, everything will go away. 2a2 will remain. So here a2 will be 1 by 2. That is 2xy, a2 is 1 by 2, 2 will go away. It will remain as, I'm sorry, a2 will be d2 fxy by dx dy. Okay, by 1 by 2. If I set 1 by 2 at 2 at 2, 2 will go away. A2 will come as a d2 fxy by dx dy into x into y. Let's settle down the third one, that is a square, a2 y square. That I have to differentiate 2 times with the y and set x equal to 0, y equal to 0. Except 2y a2, everything will go away. A2 will be 1 by 2 d2 fxy by dx dy. So we have settled down a0, a1, a2. Make sense? Now instead of a2 and x plus y whole square, I can write there as d2 fxy by dx square into x squared by factorial of 2 plus d2 fxy by dx dy into xy plus d2 fxy by dy square into y square by factorial of 2 plus now someone settle down a3 and in bracket x plus y to the power 3, that will be x to the power 3 plus y to plus 3x square y plus 3y square x plus y to the power 3. So if someone settling down a3 x to the power 3, then someone has to differentiate 3 times with the x d3 fxy by dx cube, then everything will go away. Only a3, 3 into 2 into a3 will remain. A3 will be 1 by factorial of 3 d3 fxy by dx cube, that I can substitute there. Next is a3 into 3x square y. Okay, in that fashion, I have to differentiate it with x 2 times and then differentiate with y 1 time. Then set x equal to 0, y equal to 0. Everything will go away there. What will remain there? 3 is anyway there, and then x square will become 2 and y will become 1. 2 into 1. So a3 here it will be 1 by 3 into 1 by factorial of 2 d3 fxy by dx square dy. I can replace happily there. 3 will go away. It will become 1 by factorial of 2 into factorial of 1 d3 fxy by dx square dy into x square into y. Same thing someone can pursue. This is the proof that we have received by the calculation of the dividing our volume into n different parts. We'll proceed on that. I'm really sweating. Okay, so this proof has come where we have x equal to x plus y because we are trying to divide our volume into n different parts. Where first part is the flat volume, second part is the triangular volume, third part we will see x square and like that. And with the first only we can make an assumption that one independent Taylor series and two variable Taylor series there is similarity where we can replace x with x plus y and final the base x was we can replace with x into y and then we can proceed. We will proceed again with the volume division. But just beginning of the volume division, I can solve the Taylor series through this assumption. Amazing, mind blowing. We will proceed in this. These kind of things are not available in any of the books. I challenge anyone can try. Please do not mind supporting us. +91 is the India country code. 9483160610 is the telephone number. +91 is the India country code. 9483160610 is the telephone number.